Okay, by the end of this lesson, you'll be able to describe what power is and how it relates to current voltage and resistance and calculate an electric bill. Give that one a shot. We got a guess. $40, 60 watts, 100 watts. You're welcome. Put some blue spots in your eyes. Okay, there we go. So, watts speaks to how quickly energy is being converted to another type of energy. So, like potential energy converted to heat and light. Okay, the higher the wattage, the faster energy is being converted. Electric potential energy is being converted to heat and light. Good with that. Okay. So the unit of power. Last semester we talked about work over seconds. This semester we're going to look at it as energy per second. So joules per second is what a watt is. Okay. But I introduced this equation of current times voltage. How does that end up being watts? Well, good question. So current is in what units? Amps. And voltage is in what units? Volts. So amps times volts. That still doesn't look like anything we are familiar with. Amp is a coulomb per second. A volt is a joule per coulomb. Coulombs cancel out. And you get joules per second. So conceptually, here's how this works. Voltage speaks to how much energy per electron, how much energy each electron is contributing to like the light bulb. Here's some of my energy, convert that to heat and light. Current is speaking to how many electrons go by a certain point. It's like, here's my energy, here's my energy, here's my energy. So if you know how much energy per electron there is and how many electrons per second there is, you can figure out how much energy there is per second being contributed. Into that. Tell your neighbor. Correct answer is B. Okay, just in case you didn't catch that, what we did is we took voltage is equal to current times resistance and substituted in for voltage. So power is equal to current times resistance. Good? Yeah. Once you do the same thing, but now substitute in for current. Tell your neighbor. Correct answer is, here we go there. Okay, so this A and B, I'm not going to give you. I will give you Ohm's law. Voltage is equal to current times resistance, and power is equal to current times voltage. These are handy, but not necessary. Like you can make them yourself. Does that make sense? Yeah. Up when you have something. Tell your neighbor what the answer is. Here we go to C. Next. Correct answer is, we go with B. Okay, current is squared, has more influence on power than a change in resistance. Conversation. Conversation would probably be good. This is talking through it. What do you say? Got some votes for A, some votes for B. Okay, it's true. It's one or the other. So here's one way you can do it. Start with Ohm's law. Okay, the fact that we did not change the battery means the voltage stayed the same. Right with that? Okay. So if the resistance was increased, what happens to the current? Decreases. Because voltage stayed the same. power is equal to current times voltage. Voltage stayed the same. Current went down, therefore power also has to go down. Okay. The other way you can do it is looking at the shortcut equations. We want to pick the one where one of the variables is fixed, is held constant. If all three are changing, we don't have good conclusions. So which of these two would I pick? Top one or the bottom one for ones where there's one variable not changing? Bottom one, because the battery determines the voltage. So as the resistance goes up, the power is going to go down. Good with that?
I don't see enough of that.
Have a conversation. Correct answer is? Everybody good with B? Okay, same conversation last time, except for I gave you power and you're working back to resistance. Okay with that? Your voltage stayed the same because your power supply didn't change. Okay. All right. Calculating your electric bill. I recognize this is kind of premature, kind of like how you took life and careers as an 8th grader. You're like, oh, that's great, as it should have been taken when you're like now, when you're about to go life and careers soon. So like, I recognize you're not paying electric bill, but at some point, that's gonna be a thing. I feel like you should be exposed to that a little bit, okay? So, power is equal to the rate of which energy is being converted. I've got a 60-watt light bulb. I need to figure out how much energy I'm using. So I've got 60 watts. In a month's time, I need to figure out how many seconds there are. It's a lot, just to let you know. I'm gonna go with 30 days in a month. So we got 30 days times 24 times 3,600, 2 million. $590,000 seconds. So when I multiply that, what I find that to be is 156 million joules. That's one light bulb for a month. You get charged for your whole house per month. All right. Wonderful. So this is like measuring from here to California in inches. we need a better unit. Okay? So power companies have invented this unit called kilowatt hours, similar to amp hours. Okay? So this is the only time you're going to do this, and you're kind of tipped off with this idea of kilowatt hours. You need to convert your power to kilowatts rather than watts. So we're going to divide by 1,000. So 1, 2, 3. So we have our wattage of 0.06 kilowatts, and we convert our time into not seconds but hours. So that's 720 hours. When we multiply that, we find that to be equal to 43.2. So multiplying kilowatts times hours, kilowatt hours. That's where that comes from. You see how that's much more reasonable of a number than 156 million for one light bulb on for a month. Okay? So we're given a cost of 9 cents per kilowatt hour. So I'm going to take this and I'm going to say, I'm kind of doing like a chemistry thing. I want per kilowatt hour, so I've got kilowatt hours on the bottom, and 9 cents top. So my kilowatt hours gets canceled, and I'm left with $3.89. You will have to do a problem like that on the test. If you want to take a picture of that, that's totally fine. Okay. It's also being captured on the video. Yep. Calculating your electric bill. Good. Correct answer is, or tell your neighbor, tell your neighbor.
Yeah, you know what? One of them's right.
Correct answer is, I left that up there just for your benefit for this question. This is what they sell us. Okay? Power is the rate at which energy is being converted. Okay? If you're being charged for water, you're not being charged how quickly you use water, you're charged for how much water you used. Does that make sense? Same thing here. I don't care about how quickly, that's just how quickly the numbers are changing. You care about how much water is being used. Okay with that? Okay, how much energy is being converted. Okay? So, let's talk about light bulbs. So, the incandescent light bulbs Here's a 60-watt light bulb. This is normal. This is what we usually have. Like, that's the normal brightness, okay? There's been a lot of good engineering that's happened so far in the course of your lifetime. We've had these fluorescent light bulbs, okay? These were 10 years ago, like push, maybe 20 years ago. 20 years ago, push, like, hey, these are like great for the environment. They use less electricity because these incandescent ones, the old school vintage ones, super inefficient. Like, of the energy that they use, 5% goes to light, 95 goes to heat. One office building in New York actually designed their heating system around these light bulbs, and they would leave them on in the wintertime over the night to heat the building. It was actually a really good plan until they discontinued making these ones. Okay. So these fluorescent ones were sold like, hey, these are super inefficient, or super efficient, they're good for the environment. They are way more efficient than these guys, but they're filled with mercury, which is horrible for the environment, okay? So be cautious when someone's like, it's green, it's so good for the environment. Like, be skeptical, okay? Especially if they're trying to sell you something, okay? So what we've landed on are LED lights. So LED lights, light emitting diodes, okay, just normal light. I mean, they look like a normal light bulb. They aren't gonna have to be. As new construction happens, this screw-in like light fixture is gonna go by the wayside, because it's not efficient, but houses are built with them, so. Yeah, so you pop this off. This isn't a filament, these orange things are your LEDs. Okay? I'm gonna turn them on and blind you. So like squint. Well, camera people, sorry, you're not gonna be able to squint very well. Okay, so I'll pass these around. Those orange things. So pass that around. So have you heard of, like, we've got the semiconductor plant coming in, okay? If you want to stick around the area and you want a job that's good, semiconductors has a future here in Lafayette. Okay? If you're like, yeah, I'm okay with math and science and I don't really care what I do, like I just want a good job, this could be a good job. Okay? So through the School of Polytechnic, that's kind of they're gonna run with this semiconductor thing. So LEDs have a lot to do with semiconductors, so watch this video.
One of the most common ways to generate light nowadays is by using a light-emitting diode, or LED. Like the rest of the diodes, as we saw in a previous video, one of its characteristics is that it only allows the passage of electric current in one direction. But we didn't talk about why they emit light. So in this video, we will talk about LED lights have several features that make them one of the preferred options to illuminate. such as having low energy consumption, greater impact resistance, and a longer lifespan, and because of this they are available in many different formats. But instead of going directly to analyze an LED, we will start reviewing how a common diode works, because in theory these can also emit light. It's just that they do it in an inefficient way. If we have a circuit with a lamp and a power source, energy will pass freely. This is because electrons can move freely between metal atoms and, when connected to the power source, they are forced to move. By adding a diode to the circuit, and depending on its position, the current can pass freely or be stopped. And the reason why this happens is because of its composition. Inside the diode, there is a semiconductor material such as silicon. More specifically, two types of this material. If we took a piece of pure silicon and saw its atomic structure, we will find that each atom has 4 valence electrons, which are shared with the other 4 silicon atoms around it, forming a crystalline structure with covalent bond. That is, they share their electrons, so there are a total of 8 valence electrons per atom.
Is your cable internet slowing you down? Are you falling a step behind? And are you out of sync?
Come on.
Resembling noble gases, the most stable elements known to humankind. If you don't like chemistry, don't panic. The important thing here is to understand that 8 electrons per atom is the magical number that keeps everything tightly connected. In fact, they are so connected that when a new electron wants to go through silicon, the electrons that make it up cannot move, hindering the flow of current. However, this can be changed through a process.
You guys heard of Silicon Valley? This is why they're called Silicon Valley. And all that stuff they're semiconductors.
It's known as doping, in which impurities are added to silicon to control its conductivity and convert it into an N-type or P-type semiconductor. If we add impurities that have 5 valence electrons instead of 4, then we will have atoms with a total of 9 electrons. And since 8 was our magic number, we could say that one of the electrons will be left over or be freer than others, which will allow it, when connected to a power source, to move and act as a conductor. This alloy is known as N-type semiconductor because it has excess electrons, which, let's remember, have a negative charge. On the other hand, if we do the doping with impurities that have 3 valence electrons, we will have atoms with a total of 7 electrons. This means that we would have a gap, allowing electrons to move through it and generating a movement of the gaps in the opposite direction. Since this alloy would have 1 less electron than its stable form, it would have a positive charge, and it would be called a p-type semiconductor. Moreover, to simplify the visualization, we will say that each hole corresponds to a positive charge. This way, when a p-n junction is generated, depending on the polarization of the voltage source, there will be 2 possible results. If the positive pole is connected to the N-type semiconductor, and the negative pole is
Okay, so a diode, electricity can only go one way.
connected to the p-type semiconductor, the holes and free electrons will move away, preventing an electric current from being generated. This case is known as reverse polarization. On the other hand, if we reverse the polarity of the voltage source, the free electrons of the N-type semiconductor will be able to jump through the p-type semiconductor and close the circuit, allowing the passage of the current. This case is known as direct polarization, and it is precisely here that the physical phenomenon that produces the emission of light occurs. If we return to our visualization of the atomic structure, and we focus exactly on the point in which the 2 semiconductors make contact, we are going to find that electrons are being moved from an atom with more valence electrons to an atom with fewer valence electrons. This is extremely important, because this difference in the amount of valence electrons is also related to the amount of energy that they possess. In other words, an electron that is in an atom with 5 valence electrons has more energy than another electron in an atom with 3 valence electrons. This means that, every time an electron crosses this junction, there is energy that is being lost. But as the law of conservation of energy says, energy cannot be created nor destroyed, it can only be transformed. And in this case, the energy that the electrons lost when jumping from one atom to another became light, or more specifically, photons. The fact that this happens at the atomic level has another implication. Since electrons move always from an atom A to an atom B, the amount of energy transformed in each jump will be constant, which in practical terms means that the emitted light will always have the same wavelength spectrum. This also implies that, by changing atoms A and B, that is, the impurities within semiconductors, we can emit lights with different spectra. Referring specifically to the visible spectrum, we can emit different light colors. At this point, we already know how the light is emitted, but we still don't talk about why. If this phenomenon occurs in a common semiconductor diode, we don't see them shine continuously. There are two main reasons. The first one is that in many cases our eyes are unable to see the spectrum that is being emitted. I couldn't find an exact demonstration of this, but I did find a video in which a solar panel emits infrared light when applying a voltage, and a diode generates a voltage by being enlightened, all of which is related to the same phenomenon. The second reason why a common diode does not shine is simply the shape. If we think the light is being generated only at the points where the two semiconductors are in contact, how are we going to see them if for the most part this area is being covered? In this patent in which they describe one of the first light-emitting diodes, the solution is extremely simple. Move the semiconductors away from the connectors so that they do not cover the emitted light and reduce the thickness of one of them to such an extreme that light is able to pass through. In a way, we could say that this hasn't changed much to this day. Let's analyze an LED from the inside out. The first thing we will need is a substrate where we will put the rest of the materials. To this, we add a layer of N-type semiconductor and then another thinner P-type semiconductor layer. The order is important because the transformation of energy occurs when reaching the latter layer. Then we add some cables so that the electric current can flow between the semiconductors and the light is emitted, being extremely thin so it doesn't cover it. Technically, only with this we already have a functional LED. But to be more efficient, we will add a small reflector to direct the light, which will be integrated in one of the electrodes. And before covering everything in a transparent epoxy resin, so that the set is more resistant, we will add one last element, a layer of phosphorus, although this is used only in some cases such as...
That was the orange stuff that you saw on the LEDs.
white light. In
Make
this
it
particular
warmer.
case, the diode is actually emitting a blue light, which upon impact on the phosphorus layer, causes this to emit a more yellow light. The mixture of these two spectra is what generates the perception of seeing a white light. The last thing I want to talk about is RGB diodes that can produce multiple colors. Although the truth is there is not much mystery left to it. The RGB name refers to the colors that compose it: red, green, and blue. Well, indeed, within this type of LEDs there are 3 pairs of semiconductors specifically selected to produce each color, and by independently varying the voltage that passes through each of them, the perception of different colors is generated. I remind you that there are several more animations on my channel in case you wanted.
Good. Got a worksheet due tomorrow.